Hello, everyone. You're very welcome to our first EMEA virtual meetup in a while, where Alexander Polonsky, co-founder and VP of Bloom, will present on elastic extensions for importance ranking and data exploration. My name is Nisha, and I work on our DevRel team, and we're delighted to have those of you here who are joining us live, and also those of you who are watching this after the meetup has been recorded. If you're interested in watching any of our upcoming webinars and other virtual events, the QR code, David, you're very quick, should appear on the screen, and also the link as well. Following the event, we'll also include some links to direct you to how you can get involved in speaking at a local meetup or virtually like Alexander's doing. And if you have any questions for Alexander throughout the presentation, please comment, and we will answer those throughout. You don't need to wait until the end for Q&A. For now, I'd like to introduce David Pilato, our developer advocate, who's assisting us today, and he will say hello, and then we will have Alexander kick things off.
Perfect, thank you, Nisha. Yes, I'm David, and I have been working at Elastic for more than 11 years. I met Alexander a long time ago within the French community, and we met again recently at a conference and spoke together about what he is building nowadays around Elastic. So we thought it would be a nice topic for a meetup. So here we go. Alexander, I will let introduce yourself, and the stage is yours.
Hello, everyone. I'm Alexander Polonsky. I'm Vice President of Research and co-founder at Bloom. I've been very interested throughout my career in the problem of improving access to information. And this is what we've been working on a lot at Bloom as well. And so this is what I would like to share with you, get your feedback to see if what we're doing is also has a broader interest in the community. Bloom is a small company in France. We've basically our main focus is on social media analysis, which we provide to various industrial and institutional actors. So big groups, international groups like Samsung, France, American Express, OMH, etc. And we also have some strategic partners with very large companies in France, such as Airbus and Capgemini and Dassault, as well as with some academic institutions like IDIAB, which is a research institute in Switzerland. For a company of our size, we've actually been investing quite a lot in research, both internally and also via external research partnerships. We've positioned our activity really around social media and the technology, social media data. And the technology was sort of a secondary thing to it, which was necessary, but it wasn't the focus of the company so far as a separate product. But now we are actually working on changing that, and so expanding our positioning not only to also include a generic sort of technological platform that can be used for data other than social media. In this effort, Elasticsearch is we're huge fans of the product and the community, and it's a core part of our platform. But we've built additional components around that, which we use extensively, which were really necessary for us. And so one of the purposes of this presentation is to share them with you and see how if that evokes broader interest outside of social media data environment. So our vision of information access is summarized in this slide. We basically found there are 4 major modes of accessing information. Search is one of them, but it's the main mode of access to information that we have. But there are also 3 others that have been a bit underserved, we believe, on the market so far, which is data exploration. Basically, when we don't know exactly what we're searching for, but we just try to understand what is there in the corpus of data that we have. The recommendation, where something is, we're not searching for anything specific, but the system can figure out what is relevant and recommend things to us automatically. And finally, alerting, where we don't actually do anything at all. We're not even in the system, but it sends us notifications when relevant information appears in the data set. And so there are also 4 major technological boosters, so to say, that underlie these modes of access, which is that we need to rank the information, we need to structure it, and then those have been around for a long time, and lately there's been also sort of new boosters, relatively new, which are creating an alternative representation of data in a mathematical vector space, and also the large language models, which contain generic models of language and can be quite powerful tools also to improve access to information. And so the challenge is basically how to orchestrate these enablers, the technological enablers, in order to optimize the information access experience. Now, at Bloom, we work on all these things in various degrees. Today, I won't be able to cover it all, so I'm just going to focus on the left part of this diagram, which is going to be already pretty ambitious. So one of the generic needs when we're talking about ranking information, either for search, exploration, or for other needs, is to figure out what information is important, right? That's sort of the basics of what ranking is about. But strangely enough, we haven't found a comprehensive generic information importance model anywhere, and so we kind of had to create it ourselves. So this is a conceptual part of the model, which is extensible, because obviously information importance, there's some significant subjective aspect to that notion. But we have identified sort of 4, once again, 4 for some reason, major aspects of what constitutes importance of information. So there's a relevance axis. Obviously, if information is not relevant, it's not going to be important. But how you define relevance, it can be quite flexible and extensible. So there's common, lexical relevance. Defined in lexical search, whether to what extent a document corresponds to the query that we've inputted. There's also a more broad semantic relevance, when we try to figure out more broadly relevance to concept that is behind the query. There are also other types of relevances, such as temporal, to what extent information is fresh or outdated. It can be geographic, to what extent it's close to where we are. It can be reliability in the sense of, trustworthiness of the information that we obtain, etc. Then the second axis is impact. To what extent information actually has real impact in the world. There are different ways of modeling that. It can be based on the extent of use of this information. Has the document been read a lot, or clicked on a lot, or commented a lot, or validation if somebody is given it some sort of an evaluation like 5 stars or 100 likes or whatever. There can be also indirect use inferred through backlinks, such as PageRank algorithm that takes that into account. And there are other metrics depending on what type of information we're looking for. It can be the centrality of certain actors in the actor graph, interaction graph, etc., etc. So different ways of defining impact. Same goes for entropy, which is another axis that will take into account, for example, the diversity of the search results that we obtain, but can also take into account other types of unusual things. I mean, this axis is based on the theory of information that basically posits that the real information is in the change. So things are constant. We're not learning anything. And so the variety or exceptionality of information is also a part of why it can make it important. And finally, the level of generality that we need. We can look for something relatively general or relatively specific, more expert type information, for example. Things in general that happened recently or specifically in a specific day, if you're looking for an event, etc. So all these things are ways of evaluating importance of information, and in order, in the end, what we're looking for when we do search is basically a list of information objects ranked by their importance, and so there's just one rank, and so we need to take out all this variety into account and aggregate it together in a mathematically and statistically proper way. Also taking into account the fact that all data is not necessarily the same, right? So it can come from different sources. For example, at Bloom, we have data coming from the web, but also from Twitter or Facebook or YouTube, and they're not all equivalent. And that also needs to be taken into account. So this is sort of an overall conceptual overview of the model. And now when we do this type of aggregation, there are basically three main patterns that exist. One is that we use one axis in order to filter information, and then we use another axis to actually rank it as something called reranking. A second pattern is fusion, when we have multiple ranks that we need to fuse into a single one. So that's sort of the classical aggregation. And then the third pattern is actually a mix of the two. And so I'll give you some examples of real life problems that we faced for which we needed to come up with new methods that we didn't yet find in Elasticsearch. And so this is, for example, a project during which we tried to. It was during riots in France, and we were trying to identify where the fires were, taking place to warn, basically, for security reasons, and. So this is just an example of the search where we put the query fire, and we see that thanks to the semantic search that we've put in place, where we basically use Cohere API to obtain the corresponding vectors of both the documents and the query, which we then index in Elasticsearch. And this is the result of that search, and so we can see that it's working. It's working pretty well. For those who don't speak French, so feu here is fire. So all the queries, all the results here that are shown are very 100% relevant to the query in question. But as we scroll down, we would find that actually gradually there will be documents that are no longer relevant, but they have they have scores, semantic relevance scores that are not zero, because everything in the world is somehow connected, and the system doesn't know at what point things become really completely irrelevant. And this would be fine if we were just looking at some sort of, looking at most relevant, semantically most relevant documents. But what we care about is not just semantic relevance, but also the impact. And the impact is judged by engagement, because what we want here is to prioritize documents that are that generate a lot of engagement. Means it's probably a major file and it probably is something that is confirmed by multiple people, witnesses, etc. And so probably needs to be addressed more urgently than just something that's reported by one person, or maybe it's just a question, or just talks about fire, but it is not necessarily an indication of fire. In any case, so if we were just to rank these results by impact, we would get lots of noise. That's completely relevant, and that's not what we want. Now we're using the semantic search with the idea of, and it's a multilingual, as you see, search with the idea to improve the recall, right? So to be able to find documents that talk about relevant topic or concept without actually mentioning the keyword in question. So the goal is to increase the recall, but without killing the precision, right? So if most of the results are going to be noise, that's not going to be helpful at all for our consultants and analysts. So that was a really major problem, and what we needed to do is to find a way to basically cut off the noise automatically, coming from different platforms and different languages. And so the performance of the vector search, semantic search varies, as you probably know, from one language to another, from one data set to another. And so setting a single threshold for all data in our platform was not going to work. And also these data are dynamic, they change over time. And so manual threshold setting is something that was not really viable for us. So we needed to come up with an automated way of doing that. And that was a major challenge because we needed to automatically be able to measure the precision of the results without manual labeling and obtain consistently high precision, because obviously if we can measure precision, but the precision is very poor, then none of it is really it loses all its value. So, and what we found is that basically, in order to measure precision, the only method that existed was to manually label the results as relevant or not. And also, the precision that we did observe was by default was pretty inconsistent depending on the query and the data set. So those are the problems that we've addressed, and we were able to obtain quite promising results. So we've tested a number of queries that were manually modeled from real projects, and so our approach was to basically use the actual lexical match as the proxy for manual labeling of relevance. So given that the queries were pretty well modeled, in our case, in any case, we could take these queries and we could expand them using a large language model, and then use this labeling to say, okay, well, for this query, this is the relevant data. And so we would do that for a number of queries, and it allowed us to come up with the score threshold that was required to achieve the necessary precision of the results. So we knew that we needed to cut off anything below a certain score would basically bring too much noise in relation to the signal. So we managed to increase the recall without killing the precision, with maintaining the precision at the required level. And so other things that we did in order to arrive there is we noticed that actually the longer documents tended to receive lower scores. And there was a bias due to the document length, which did not reflect the reality. So it was just the bias of the due to the vector search per se. So we corrected that bias by normalizing on document length and normalizing the score on the document length. And also, not surprisingly, we found that the rank fusion produced better results than just using semantic search alone. So fusing the semantic rank with the lexical rank allowed us to obtain higher precision, sufficiently high precision in the end. And so this brings us to yet another problem, which is the rank fusion in general. So how do you actually fuse ranks in an optimal way? And here, once again, we needed to develop a new approach because basically what exists out of the box in Elasticsearch is reverse rank fusion, but it's highly insufficient for our purposes. Reverse rank fusion was developed a number of years ago in the context of fusing various lexical searches. And even then, the model itself we found was highly dissatisfying, given that it was just based on intuition of some couple of engineers. There was no real justification for it from a mathematical point of view. It was not really extensively tested in that paper either. And so what we found is that it actually works pretty poorly, even on certain reference data sets like MS Marco, which is a common data set to test ranking algorithms. And it actually performed worse than just semantic search by itself. And also in our data, we found that it didn't work well. So we looked into that a bit, and we found that actually reverse rank fusion, it was just looking at the pattern of the formula, we could see similarity with the ZPath law, which is actually, unlike reverse rank fusion, is a much better founded mathematical model. It's a more general mathematical model. It has an extra parameter, so it's actually not such a huge step from reverse rank fusion. So they did have the right intuition in a way, but adding that extra parameter does improve the results significantly, and more than that, it justifies actually a linear approach to normalizing the ranks using min-max, for example. However, what we observed is that the ZPath law, so the lexical rank follows it very well, but semantic rank only follows it starting from about half, the top half of the scores. So starting from around 0.5 upwards. Which is fine, but it is important to consider when you're doing the normalization of the ranks. And so in the end, what we needed was a generic aggregation model that could take ranks from any number of ranks from the importance model I presented earlier and aggregate them together. And reverse rank fusion definitely was not going to do that. And so, well, there's a sort of a classic model, it's a weighted average. It's not a very sophisticated model by itself. The trick is to figure out what weight and what average, right? So, basically the weights will depend on the quality and the relevance of the various ranks that are part of the aggregation formula. So if semantic rank works really well in relation to lexical one, it should receive higher weights, and inversely for the given data set and the given algorithms, set of algorithms for individual ranks. So basically, and also the average, it can be arithmetic average, but it can be also geometric average with multiplicative logic, or harmonic average, or many different types of averages. But, well, not too many, but thankfully, but there are still a number of them which change dramatically the final results. So these are not minor considerations in any way. To have solution to that was not something trivial. And so once again, we used the expanded lexical match that I described on the previous slide as a proxy for manual data labeling, which allows us to find the optimal weights, in particular when fusing semantic and lexical search together. But obviously, this approach will not work in a general way. When we talk about, let's say, fusing impact ranking with relevance ranking, there is no real objective sort of relevance labeling for this type of aggregation. So the only way to solve that is really from user feedback. But we can still have some generic conceptual approach of how these ranks should be aggregated. And for example, relevance and impact intuitively should not be aggregated in an additive way, right? So if something has zero relevance, even if it has a lot of impact, it should have zero importance in the end. It should not appear highly in the aggregated ranking. So it should be based on some sort of a multiplicative logic, and this is basically what we've implemented. So this is what this finalizes the presentation of the ranking and search part of the extensions. And now we can proceed to the data exploration part. So for data exploration, basically the objective is to find, when you have a big corpus of data, you want to understand what's in there. Generally, this corpus of data can be a full corpus, but it can also be just outcome of a particular search as well. So you could, the search and exploration are modalities that are complementary and can be definitely used in a integrated and interactive way, where you can start with search, then use exploration to explore what's in search results, then use the exploration to refine your search, etc. Or you can start with exploration and say, okay, I'm interested in this, I'm going to do some search, more involved search around that topic, and then explore the search results, etc. So so the goal is, whatever the data set, whether it's the full corpus or the search results, is to find is to generate automatically some kind of an optimal, simple and synthetic representation of this data. And the only way that this has been attempted, as far as I know, is through generating what's known as word clouds. And it's highly unsatisfying representation for a variety of reasons. And there are even best practices that say to never generate word clouds. But because they can be quite misleading. But in any case, what we've developed at Bloom is something, a much more sophisticated version of that, you could say, which is a term graph that automatically searches, extracts the most important terms from the data set. It's not necessarily what's called entities, it's terms in general. And it ranks them by importance according to our importance model. It takes into account multiple dimensions such as semantic relevance to the given context, but also impact, different types of impact, such as aggregated impact over the period of time, or potential impact to detect also weak signals, and also distinguishes importance, impact, as sort of directed by the producers of the information or by the consumers of the information, so which is not the same. So, for example, somebody may insist on using a certain word, but a certain term frequently, but it doesn't make it necessarily important if the readers don't react to it, if they don't like it, if they don't validate it somehow. And so what you're looking at is what we call a term graph, where each node is a term. So you don't see all the terms from data set. These are only terms optimally selected, so ranked by importance, and then with a certain threshold that has been found to be meaningful. And each edge in the graph or connection between the nodes represents the number of co-occurrences between these terms within the same sentence. And so this graph represents the corpus, the main subjects of conversation, the topics of conversation, and very quickly we can understand what this is talking about. This is from a project on sustainable fashion, and the terms that you see are the most important terms from the conversations around that. And this is already something that our analysts use on a daily basis, and it allows them to further structure the information and derive meaningful insights from it. But we can go a step further.
Alexander?
Yes?
Yeah, I do have a question about this graph.
Sure.
If you allow me. So we can see a lot of dots. Is the distance between the dots mean something?
Absolutely.
Okay.
So each edge represents the number of co-occurrences, and the stronger the connection, so the more frequent are the co-occurrences, the more the two terms will be drawn together.
Okay.
Closer together. And so, yes, the positioning is very much important. It's a very good question. So the terms that will be also in the center of the graph are the ones that are central to the conversation. And the terms that are more on the periphery will be more niche terms, more peripheral terms.
Okay, thank you.
So we can go a step further and ask the system to automatically cluster this graph and discover the topics, the main topics, completely automatically. So, and this is what we implemented at Bloom. It's a new methodology, and that we found works much better than existing topic modeling approaches. And what it does is that it, based on the term graph, it clusters these terms in a non-exclusive way. So the same term can belong and does belong actually most of the, very often to multiple clusters. So it clusters it in a high-dimensional space, not in a two-dimensional space that we see that is used just for visualization. It identifies within each cluster the top up to 3 most important terms and up to 5 most important sentences, numbers that we found to be the most optimal in terms of precision and recall of the end results. And we use the LLM so this is a statistical analysis so far, and then we use the LLM just for the final step of coming up with a label. So the fashion industry pollution is the label the LLM came up with automatically based on the cluster properties that are displayed on the left. And it very much reflects what the topic is about. And we don't, so this method does not require specifying the number of topics. It's something that the system determines automatically as well based on the metrics of cluster quality that we've defined. And so what we've found is that the performance of our method is comparable to human performance. It's not equivalent in a sense that when our analysts manually analyze the term graph here, they would come up with a similar number of topics generally, actually, but they would maybe aggregate a few topics together or break them up, on the contrary, to more fine-grained topics. They would detect certain topics that the system would not detect automatically, and vice versa. So the structure is not exactly identical, but it's equivalent in quality in the end. So when analysts look at the two results, manual versus automatic, they cannot say which one is necessarily better. I mean, the manual one is objectively better, I mean, in general, but manual one is going to be more relevant in the end because the analyst does better understand the project objectives. And as there are many ways of structure information, the way you actually do it with a specific goal in mind is going to be different depending on the goal. Yet, having this automated underlying structure is something that covers easily 80% of the effort required to then restructure it slightly and arrive at the final result that's the same. And also this type of effort approach can be used. So we structure the information in order to do statistical analysis afterwards. But obviously, you can imagine to use the same structure for example, faceted search. To filter the search results, for example. So this is it for me. I don't know if there are any.
Thank you so much. So there is no question so far on the chat, but feel free to ask your question. You can. By the way, I'm adding here also the links to the company. So one of my question is actually, how do people can try what you build? Do they have to contact you and enter with you in, I don't know, discussion, something like that, to have access to this power?
Yes. So basically, these are the components that we've built internally and we use internally so far. And as I said, that they're built on top of Elasticsearch. Which is the underlying engine. for accessing information. So the goal of this presentation for me was to gauge your interest of the community in these components, and engage in conversations around that to see what kind of model we can adapt in making these components more broadly available. So I've kicked off internal discussions about open source models, which are ongoing, but the decision of open sourcing something or not really depends on the underlying business model. It depends on the amount of demand that exists in the market. So it's not something that we can decide on a priori. And I would welcome any feedback that you have, either in terms of the usefulness of the approach, or any kind of suggestions or use cases that you may have on your side on which we could test and see how this works outside of social media data.
Okay. So I don't see any other questions coming. So I guess we are done, I guess.
Thank you so much, Alexander, as well. This presentation was originally given in French, so it was great to be able to get it in English and get it out there into the world as well. So thank you so much.
Thank you very much.
Have a good day.
You too.
Goodbye.
Goodbye.